image, SEM image is taken, and they have observed that the wings behave as a natural photonic crystals. Okay, so they have the we can say nanophotonic phenomena. Okay, in the presence of light. So next example is basically a nanophotonic in peacock feather. Similarly, we can say it shows some nanophotonic crystal behavior at high frequencies. Okay, so next let move towards the first initial we can say 30-minute discussion on the some based upon their physical phenomena at nanoscale. So we will focus on nano-optics, okay, few introduction and few technical terms, because in my paper or in my work, I will use that directly, okay. So let's see why we, what is metal optics and what is there, we can say problems at with optical fibers and why we are shifting to the waveguide. So all such I summarized in this slide, okay. So if you see the majority of optical components, okay, as I told in the starting slide also, basically based upon your dielectric, okay. Even if you talk about your optical fiber, so we are using dielectric core, okay, and claddings, and then we cover it with the material to avoid from the surrounding environment, okay. So now problem, let's see what are the problems. So basically there is a issue of diffraction limit, okay, and also there is a problem of bending loss, more bending loss in the optical fibers. So these two problems I have tried to show here in this slide. You can show there whenever there is an input is provided to this fiber, and due to bend, okay, so the velocity of light at the bend will not cope up, and there is the losses, okay, across the bend, and you will get some uh, output, very minimum output, and then we have to use the optical amplifiers to amplify. Okay, so this is the one issue. Next issue is the diffraction limit, as I told, because whenever the light is fall on this optical fiber using total internal reflection, so there is a particular, we can say, minimum mode size, okay, or mode, we can say optical mode must be there for the propagation. You can see roughly I have drawn that maximum strength is in the center, and then it is exponentially decay out, okay. So even if you observe in this diagram, so there is a some mode size, okay, and the optical mode in a, we can say, this type of waveguide, or we must be greater than lambda naught, where lambda naught is the operating wavelength divided by 2 times the n core. So this is the optical mode size, and if you not use this condition, then the mode will decay out and you will not get the output. So we can say that there is a some diffraction limit, okay, for the optical fibers. And as you know that we are reaching towards the limit of Moore's law as well. So because when you use the you reduce the further the diameter of this core, okay, so we cannot say handle this optical modes efficiently, and so for this we have to move toward other technology, that is the plasmonics, okay, that I will show in the upcoming slide. So even I have shown through this solution. So some solution is some student, we can say scientists, they are using the photonic crystals, okay. So you can see using some photonic crystal and defects in the photonic crystals, we can handle the modes efficiently. We can say EMF waves in a photonic crystal waveguides. Okay, so what we can see that if you are using the dielectric component, so we will have high speed, high bandwidth. Okay, and but for the large scale integration, we have to shift towards the advanced technology like plasmonics, okay, nanophotonics, that we will see. Okay, so before moving towards this nanophotonics, so there are few more terms like plasmons, polytrons. Okay, so with some simple diagrams, I will tell, because our sensor is based on this, we can say, metal dielectric components only. Okay, and so we must know what are the plasmon, bulk plasmon. One by one, we will see. Let's see what is the plasmon first of all. So plasmons, basically we can say, if you compare the electrons, okay, because you know electrons are the free particles, okay, that move around the, we can say, nucleus. So we can compare this simple model with the gas model. So we can say electron gas in a metal and real gas molecule. So we are relating the that movement of the electrons, because you know the movement of electrons will change with position and time. So we are comparing with the gas molecules, and based on this we will apply some model, and we will calculate the what are the we can say minimum conditions, okay, how it behave at high frequency. So for this, we can say metals are expected to allow for electron density waves. So that electron density wave is nothing but the plasmons. Okay. So also let's move towards the bulk plasmon. So if you talk about bulk plasmon, so we can say that metals allow for EMF wave propagation above the plasma frequency. So this how this plasma is coming, because we are relating this electron as a gas model. So there is one plasma frequency omega p, and how to calculate that we will see in the upcoming section. Okay. So basically we can say that in a single line that metals, they become transparent at the plasma frequency. So this is a, we can say, common single lines answer to this question. Okay. So next is surface plasmon. If we move towards this one more advanced term, surface plasmon. So if you see this dielectric and metal configuration, okay. So usually at high frequency, or we can say an operating frequency, here the permittivity of your metal will become negative and dielectric is positive. Okay. So when the light will fall on this structure, so it will create some plus minus region, and oscillations of, we can say, electron will take place. Okay. And you can note that if you use this geometry, that is metal dielectric, and this will support only TM wave. Okay. And if you, next is question arises, the very important is the field strength. Okay. So that is how we can observe the field strength. Okay. So you can see there is a graph, okay, intensity with respect to the position, okay, axis. Okay. So you can see that the strength is exponentially decay out. Okay. And the strength in the dielectric is more as compared to the metal, because there are ohmic laws in the metals. So due to this only, strength is very less in the metal side, but more in the dielectric side at the high frequency, right? And sometime the people given the name, okay, surface plasmon polytron. So if you have the strong coupling, okay. So these are the few technical terms, right? And now let's shift towards the, again, next important topic, that is the local field intensity. Okay. And how it depend upon the wavelength. So that is behavior we will see, uh, because in the previous slide I have only show you the intensity and with the position. Now what is the we can say role of wavelength for this type of structures? For this wavelength, in this slide I have taken both long wavelength and short wavelength. Okay. So, and we will compare this to structure, and we will see the importance of this intensity on the wavelength as well. Okay, one by one. And because this will decide the various application in this nanophotonics. So first, let's see the case of long wavelength. Okay, so you can observe that we have again metal dielectric structure, and you are operating at a long wavelength. Okay, means less frequency region. Okay, so you can clearly observe that the confinement of these modes are very poor in this type of long wavelength. But for the short wavelength, you can see it is a very highly confined. Okay. And also if you see the strength, behavior, intensity of two different region, so you at we can say when the device dimension, okay, is comparable less than to the operating wavelength, then only this phenomena will occur. Okay. And the intensity is better at the shorter wavelength. Okay, means higher frequencies. So due to this region only, we are this type of waveguides have better application towards the shorter wavelength area. Okay. So if you see this characteristic now based upon this discussion, so if you this type of, we can say, EMF waves show strong localization. Okay. And also the high local field intensity that is easy to obtain using this type of nanostructures. Okay. Now if you talk about the applications, so we can use this type of guiding structure below the diffraction limit. Okay. So means there is no limit on the this mode size. Okay. As like we have such limit in the optical fibers. So you can see guiding is easy. We can say below the diffraction limit, some we can use some low linear materials for the low linear optics as well. And next is the sensitivity optical study of surface and interface. And next application is the biosensors, or different types of optical sensors can be designed using this type of nanostructure. Basically, this metal dielectric nanostructure is very, we can say, uh, uh, 10 years back they have proposed. Okay, but now we have advanced structure as well. We can use hybridization in the waveguide as well. So that I have also discussed one by one. So again, I was discussing about the gas model. So in this one slide only, I will summarize, okay, that gas model and how the plasma frequency can be calculated for such nanostructure. So that is therefore I given the name metal optics in metal insulator metal waveguide structures. Okay. So as I told, if you have metals and if we go towards the atomic level study of such nanostructures, so we can say that the metals are lattice of positive ions, okay, that is surrounded by the equal number of electrons. And this electrons, as I told, changes with the position of this electron change with times. Okay, so randomly they are moving, and we are relating this situation with the gas model. Okay, so therefore, free electron oscillation, we can say it obey 1D equations. Okay, that is the mass of the electron. Okay, a second order derivative of position, that is x with respect to time. Okay, plus m gamma and x basically is there and equal to minus E is a charge and capital E is the electric field. So this equation is there, 1D equation is there, that will we can say support this movement of the electrons across the positive ions. Okay, and here as I told, capital is the electric field, so we can say we can relate with the equation E naught e raised to power minus I omega t. Okay, so this is basically external field, and then m is the mass of the electron, and gamma we can say is the collision frequency of the free electrons respectively. Okay, so based on this we have to solve this equation. Okay, and we can calculate the position. Okay, so x we can calculate, so you can see so x is equal to minus a charge on electron divided by m, and there is a product of omega square plus I gamma omega e. Okay, and one more parameter is the basically permittivity, and permittivity of metal we can also extract from this equation, and it is minus omega p. Now you can see omega p is the plasma frequency of the electrons. So this is very important term that will decide whether you will have the propagating modes or the lossy modes. Okay, so it is minus omega p square divided by omega square plus I gamma omega. Okay, so this is a very we can say common equations that are used in this plasmonics. Okay, and next, if we one more thing, you can see that the plasma frequency is related to your concentration of the electrons, capital NC, into E square divided by epsilon naught m. Okay, so this is the equation, that is, if you put the values, we can get the permittivity of the metal. Okay, so next, let's move towards the sub-wavelength mode theory. That in the optical sensors, you must know what types of modes are supported. Okay, so now the type of, we can say, waveguide that you are using. Okay, so will decide the polarization in the waveguide. Okay, so basically in the starting also I have written, if you are using metal dielectric structure, so you will get the only TM waves. Okay, so but if you are using the simple dielectric waveguide, then we can have a TE as well, propagation. Okay, if rectangular waveguide if you're using. So let's see what type of modes are supported at sub wavelength. Okay, so therefore we can, before starting again, I have defined here SPP, that is surface plasmon polytron. So that is basically a coherent electromagnetic wave. Okay, so which obey the Maxwell equation, and also this equation waves will supports the, we can say, Helmholtz equation. Okay, so grad square E plus K square E equal to 0. So simple wave equation is also, we can say, supported by this electromagnetic phenomena. And next, two polarization, as I told, can be propagating in a rectangular waveguide. If you are using the dielectric, so both polarization are possible, like TM polarization or TE polarization. Okay. So next is the most important relation, that is the dispersion relation, and this will give you the some knowledge about the group velocity and the phase velocity in your sensor. We can say a nanostructure. Okay. So again, as I told, that the simple wave equation that we are studying in our BTech course. Okay, so in the third year, so same can be used to starting point in this type of nanostructures. Okay, and then again we have to get the relation of omega k. Okay, so dispersion relation is nothing, we can say it is a relation of omega and the propagation constant. And to understand its behavior, so let's start with the wave equation, simple wave equation I have taken. So grad square E, so I have expanded this, okay, equation and written in a simplified form, where you will have some refractive index and the velocity of light as well, variables are there. Okay, and if you get the solution, so for this approximate solution, it is a exponentially decaying function. So we have to substitute here the value of electric field E, ZT. Okay. So in the this equation, and later on, what we will observe that your k square equal to n square by c square omega square. Okay. So this we will get. Okay. And from this only, we will first get the omega square value. We have to transpose different terms. Okay. So you will get this final relation that is relating your omega square angular frequency with the velocity of light, refractive index, and propagation constant k. So once you analyze this in MATLAB, so you can see the relation of omega by k is look like this one, where you will get the if you, because what is our purpose is to get the behavior of group velocity. Okay, group velocity is the a derivative of omega. Okay, so with respect to k. So this this the main equation is this one, and when we will take derivative, so you will get the this type of response. Okay, straight line. Okay, and this will give you nothing but the group velocity. But one more term is there, phase velocity. So if you don't take any derivative, okay, and so omega by k value will give you the we can say simple phase velocity value of your nanostructure. Okay. So one more thing is that this, no doubt, this is the simple equations that the BTech student he can also use, but at nano, as I told, nanoscale, some behavior will change. Let's see how this can be changed, because the refractive index is equal to square root of epsilon r, right? And at nanoscale, this epsilon r is related to one more parameter, that is the susceptibility chi. Okay, so if you change put the value of epsilon r, so it is equal to 1 plus chi. So at nanoscale, your phase velocity will change to c by square root of 1 plus chi. So this is the we can say phase velocity behavior at nanoscale. Okay, so uh, so this is the one additional point in dispersion relation. So one more thing is about dispersion relation is that if you uh, analyze it, and we can get some absorption behavior of the EMF wave. So in the next slide, I have given the term title as absorption and dispersion behavior of the EMF waves. So now let's see how this relation can further help us in observing the absorption in the we can say nanophotonic sensors. Okay, so for this one, as I told, starting point, let's start from the dispersion relation. Okay, so because as I told, dispersion relation is omega k relation, and if you get solve and get the value of k, okay, propagation constant, it is plus minus omega c by n. Okay, now let's see how to get the absorbing behavior of the materials. Okay, so as I told, if you are using metals, okay, so they have a complex refractive index. Okay, so refractive index, if you see, it is n prime plus I n double dash. Okay, so it will have real part and imaginary part, and
I
then
will
we have
request
to
everyone to mute themselves. Hello? Everyone, can you mute yourself? Mandip sir, continue.
yes ma'am. Okay madam.
Continue.
So our purpose is to see the absorption behavior of the metal, right? So we have to put the complex part in the dispersion relation. So if you see k equal to plus minus omega c by n, so here substitute it. Okay, and you will get that some real part and imaginary part again in the k omega variation. Okay, so if you see and then what we have to do, we have to compare it with the some alpha and beta part standard values for the absorptions. Okay, so alpha will give you some loss and beta as well. Some we can say phase, if you want to get the phase loss, so we have to check out the imaginary part. So we have to compare with the standard relation. For example, beta, it will give you omega c n prime. Okay, so this will give you the beta value, and alpha also we can get calculate from the imaginary part. So this is the way how we can analyze the absorption of the metals particularly. And also if you get put this in your standard solution of the EMF wave. Okay, so from there only we can see what is the traveling wave part and what is the decaying part in your sensor. Okay, so because we have very thin confinement of the modes across the slot region, so this study will give you approximate behavior how your wave will decay out. So in the last only I have plotted, you can say there is a blue color line. Okay, oscillations are there and it is decay out. Okay, so such behaviors will give us the rough idea of in our propagation of light in metal dielectric structures. Okay, so in the last point also I have written alpha is nothing but your absorption coefficient, so that you can calculate easily from the equations. So same thing is there. As I told, you will have complex refractive index. So you can solve this equation in different ways as well. So you can, as I told, your refractive index is equal to square root of epsilon r. Okay, so you may sometime put the complex part or real part of your permittivity, and you know permittivity is related to chi. Okay, so such things means there are 2-3 ways in which you can analyze the, we can say, absorption behavior of the metals. Okay, and you can get the absorption coefficient alpha. No doubt in today nowadays we have software, okay, like console, and there is also numerical where we can get the absorption values, okay, loss graphs from the structures directly. Okay, so means all these softwares, they are basically working on these basic equations, they are solving and they are giving us the values. Okay, so next is the one more advancement, like how the propagation of EMF wave will take place. Okay, so we so there are few fundamental condition of the frequency. Okay, so from the, we can say, you know that the permittivity is dependent upon the frequency. Okay, so this if you plot the permittivity plot with respect to frequency, angular frequency, so you will get such type of thing, real part and imaginary part. So if you, imaginary part is nothing but your losses. Okay, so because these days we have software, we can say database are there, we have to simple put the name of the material and we will get such graphs. Okay, and we will see their behavior in at what frequency we have maximum loss. Okay, you can see, and then accordingly we can pick out the operating regions. Okay, so from this type of graph, you can see both variations have been plotted here, permittivity and the refractive index. Okay, so now let's see what will they signify. So if you have the frequency that is very less than the operating frequency omega naught, okay, so you will have high refractive index, and here we will have low, we can say, phase velocity. Okay, because the phase velocity it is a c by n prime. So this is the relation. Okay, next is the, when you have comparable to operating frequency, you will have strong dependence of omega on the phase velocity. And last is when the frequency is more than the, we can say, operating frequency, then we can say n is nearly equal to 1, and your phase velocity is equal to the velocity of light. So such we can say things we can summarize from this type of plots. Okay, so next is the, I have taken the final diagram of dispersion relation for the metal insulator structure. Okay, so because as I told, from this relation only we can see what are the dominant modes or the bound modes in a waveguide, what are the some quasi bound modes and the radiative modes. Okay, so if you, as I told, get the omega versus real part of kx, where kx is the propagation constant across the x-axis. Okay, so this graph can be, we can say, get from the console as well. Okay, dispersion plots, and we can see what are the bound modes. So for this, we have to take the reference of light line. Okay, so this dash line is nothing but the light line, and whose value is ckx divided by square root of epsilon d. Okay, so epsilon d is the permittivity of the dielectric, okay, or the insulator in your design. Okay, so you can observe that the all the modes that are on the right side of this light line are the bound modes. Okay, and the modes that are across the left side, that is the above the plasma frequency, are the lossy modes or the radiative modes. Okay, so means from this only we can see the what will be our cutoffs for the, we can say, for our nanostructures. Okay, and also it has been observed that if you are you can observe that after some certain propagation constant value, so it becomes saturated. Okay, so it will follow this dash line, that is the value of omega p divided by square root of 1 plus epsilon d. So means approximately this value can give us the saturated value, or we can say maximum range for the bound modes. Okay, so means some calculation is required, like we can also numerically calculate this saturated line. Okay, and always it is below the this saturated line, the all the bound modes. Okay, so now one more uh, uh, important chart is there. Okay, so that will help us in deciding the material for our sensor. Okay, so
Hello?
basically that is the permittivity and permeability chart. Okay, so this chart is basically we have to help this chart help us. So this chart is divided into 4 quadrants. Okay, first quadrant is basically when both the permittivity and permeability values are positive. Okay, so epsilon and mu are positive here, and here all we can say semiconductor crystals, water and air will fall. Okay, and also you can observe that in simulator. Okay, so we are taking the permeability value as 1. Okay, red color line is a constant line. Okay, so permeability value we always put 1, and we are changing only the this permittivity values. Okay, epsilon values we are changing. So you can see if we you have negative permittivity and the positive we can say permeability. So you it is fall under second quadrant, and here metals will fall. Okay, under this second quadrant. Okay, and this will support the plasma. So it will help us in we can say electrical plasma behavior at that frequency. Right? So next, if the we move towards the third quadrant, that is the negative index material, or we can say artificially materials, that is metamaterials. So both permittivity and permeability are negative here. And in the fourth quadrant, okay, so where you will observe that permittivity is positive and permeability is negative. Okay, so you will get some magnetic plasma. Okay, so but in sensor, so second quadrant is important because metal is always there. Okay, and also sometimes first quadrant dielectric is there. So we are more using first and second quadrant, and those who are working in metamaterial type of antenna sensors, they will work on third quadrant. Okay, so next the question arises means how to excite the sensors. Okay, so nanophotonic sensors, so we have to follow some different we can say methods that are available. So let's start from the initial we can say the first method that is proposed in the by the scientist. Okay, for simple SPR sensors. So what they have taken, so they have taken metal layer, okay, very thin film metal, and above that they have deposited the very thin dielectric back color line is nothing but the dielectric layer. Okay, and they are using prism, because you know for exciting any surface plasma you have to fall the light at particular some angle, like here they are using theta 1 angle. Okay, so how to maintain such angle, so we have to use prism. So we can fall light and maintain theta 1 angle, and it will uh, for some gap is there. Okay, so the name, so therefore they have given coupling gap. Okay, very small, 1 nanometer to 2 nanometer, maximum 5 nanometer we can use. Okay, so there will be coupling of the light from here to here, and oscillation of the we can say surface plasmons will occur in this interface. Okay, and so but and the name they have given as the autogeometry. So as per the scientist name, so they have proposed in the research paper, but there are few issues. So they have observed that the strength of the we can say intensity of the surface plasmon is very less due to the coupling gap. Okay, so there are more losses. Okay, so what they have done, so they scientists Krishmans and others they have proposed new structure, so where they have removed this coupling gap. Okay, so what they have done, they directly put the prism on the metal. Okay, and they have deposited dielectric on the bottom side, and again they have launched the angle theta 1, and they observe that the intensity is some we can say better in this case. Okay, so they have overcome few losses, so they have reported in the research paper. So this is one second method, and third method that is using nowadays for the nanostructures is the grating. So if you see the gratings, no doubt we are using in our optical fiber as well. So such same technique grating, that is the you can say comb-like structures. Okay, and there is a perturbation of the refractive index. Okay, can be used to excite particular wavelength. Okay, so you can see there is one media. Okay, suppose air is there, then metal is there, then you are using different comb-like structure, so we can make it a grating structure, and we can also excite some particular wavelength. So there is a Bragg relation, and we can use this Bragg conditions to excite some particular we can say modes in a waveguide. So you can see there is one snapshot I have taken from the research paper. So they are use the tapered structure, and gratings are there. So they are using scare we can say equal squares, periodic squares are there, okay, on which the light can fall, and they can excite the some nanospheres. Okay, so nanospheres that are placed where in a, we can say, periodic way. Okay, so very small gap is there between this spheres, and the diameter of this nanospheres may vary from 10 nanometer to 100 nanometer. Okay, so you can see we can excite the starting nanosphere, and it will, through coupling, it can go to till last nanosphere. Okay, and radiation of light may be there, and such uh, strength of the, we can say, intensity can be measured easily. Okay, so I have taken few we can say experimental pics from the research paper for the excitation. Okay, so you can see this is the plasmon polytron propagation in gold rod. Okay, so there is a gold rod is there, and they are exciting through laser in the wave at the wavelength of 532 nanometer. Okay, and they have taken a gold rod of 8.1 micrometer, and you can see that they are exciting here of launching the light from the laser, and light even go towards the other end. Okay, so experimentally you can see in 2000 they have tried. Okay, so this scientist they have done, and now we have we can say advanced grating, we can, as I told, gratings designs for the excitations. Okay, so there is one more way of exciting, as I told, same thing that I'm discussing here, like autogeometry and KR geometry. So such things is there. They have used prism in this plasmon polytron excitation. So they have given the launch pad name to this type of technique. Okay. So again, there is a metal. You can see we have to use a tapered geometry for the launching of the light. Okay. So there is a metal layer, and black color line again is a dielectric. Okay. And there is a prism, and you are launching the light. Okay. And we will get the again surface plasmon, and the experiment, we can say, if you they have taken the experimental image also, so they are launching and the modes are going. So, and one thing you can observe that the strength is reducing drastically. Okay, so these are the lossy modes. Okay, so so such challenge are there, then we have to amplify it and then used for the transmission. And again there is some we can say nanospheres or nanoparticles are there, so they also excite, we can say the array of 50 nanometer diameter gold particles are there and spaced by 75 nanometer. So again, they have excited and you can say coupling of this light can be possible. And this type of structures we can, as I told, we can use for sensor as well. Okay. So basically the refractive index sensors can be designed using this nanoparticle design as well, where coupling can be possible, but we are more we have to use the diameter carefully. As I told, in the range of 10 nanometer to 100 nanometer we can use. Okay, and even we can analyze in software. So what is the, we can say, behavior of the intensity of light. Okay, so you can see what are the advantages. So we can say that the this guided electromagnetic energy at optical frequency will take place below the diffraction limit. Okay, so there is no problem of diffraction limit that we are facing with the optical fibers. Okay, and also it enables some communication between the nanoscale device. So you can say coupling help us in this transmission of electromagnetic waves. So in nanoscale device like modulator switches or sensors we can use, and also the information speed and also density we can it can exceed through the current electronics. Okay, because it is purely on photons, and you know photons are massless particles, so you will have better speed and density values as compared to the nano electronic devices. Okay, so next one more phenomena is there that is basically extraordinary transmission through aperture, because some sensors based on aperture. So also let cover this in this one slide. Okay, and for this, because what the scientists have observed, if the diameter of the, we can say, this aperture is comparable to the wavelength, so we can say it is sub wavelength aperture, then there is a extraordinary transmission. Okay, so to understand this, you can see they have taken the gold film. Okay, and circular in a circular fashion, and in the center they have created some we can say 440 nanometer diameter hole. Okay, and this diameter hole is we can say surrounded by the circular grooves. Okay, so this is the, we can say, rough structure. Okay, and to understand it, extraordinary transmission through this circular aperture. So you can see they have put this diagram in their research paper, optics letter. Okay, so in 2001, you can see they have taken two metals and they have grooves. As I told, they have used circular grooves, so it will look like some space will be there. Okay, and this aperture they have shown through this gap. Okay, and again same, because it is a symmetric structure, so same thing will be on the right side. Okay, now if you launch some incident light, okay, with the wavelength of lambda, so you can observe that there is an extraordinary transmission, means the behavior, you will get some, we can say, more confinement with fast modes. Okay, so will be there. And uh, if you put some sensing media on this aperture, you will observe that there is the shift in the, we can say, intensities or transmission. Okay, so through this shift you can calculate some different parameter of sensor like sensitivity. Okay, so figure of merit, detection accuracy, also thing, means this design can also this also used by the some scientist for the sensing, refractive index sensing basically. So you can see in this research paper, so they have done experiment and they have proposed that the transmission enhancement of 10 factor, okay, 10 times compared to the bare hole is there. So you can see there is a drastic improvement in the transmission. Okay, and also 3 times more light than directly impingement on the holes. So this you can see is we have such benefits of using this sub wavelength aperture and in the terahertz range. Okay, and it is basically through the excitation of the plasmon polytrons. Okay, so now same thing is their electron gas model that I have already discussed. So in this slide I have given the full steps how I have reached towards the calculation of permittivity of the metals or even for the dielectrics. Okay, so you can see here we have to start from the time varying field equation ET. Okay, and you can see it is relating with the frequency, omega frequency, and the time. Okay, so it will change, your electron position will change with the time. So this is the equation, and then we have to use the equation of motion of the electrons. Okay, so for this we have to use the Newton's law, that is mass into acceleration is equal to force. Okay, so mass into acceleration, you can see if you are considering position as r. Okay, so it is double derivative of r with respect to time. Okay, and you will get the this equation, and from this we can put the dipole moment electron parameter. Okay, in this second equation, and we will get this finalized equation where you will have mass, dipole moment, electron charge, and the electric field, external electric field. Okay, so means here your moment, dipole moment is also a time varying quantity, and your electric field. Okay, so next is, it is a second order derivative, and we have to solve it to get the final equation of the dipole. Okay, so dipole in terms of angular frequency, we will get this equation that is equal to minus E square by m 1 by omega square into electric field E. Okay, so once the moment is known, this dipole moment, and we can put in the standard relation of dielectric constant, that is equal to 1 plus chi, and chi is nothing but capital N, that is concentration of the electrons into dipole moment divided by epsilon naught E omega. Okay, so here only we can put the substitute the value of dipole moment, and then we will get the final relation of this equation, and then we can substitute the value of omega p. So in the last, we will get epsilon r equal to 1 plus omega p square by omega square. So this is the, we can say, relation of dielectric constant. And that is usually reported in any, we can say, plasmonic sensor paper. Okay, so and one more thing is that you can see the what is the role of omega p. So you can see the omega p will decide the cutoffs for your design. Okay, so usually you can see target it, as I told, for metals it must be negative, and for the dielectric it must be positive. So such behavior we can easily observe through this relation. Okay, so all such, as I told, in there are websites are there, you can put the material name and you can get this graphs, and you can see the positive region and negative region very easily. Okay, so now let summarize it. Okay, so why we are using nanophotonic sensors with plasmonics. Okay, so for this, the only the reason is that the operating speed. Okay, if you see with respect to time, so you can see in this graph they are taken from year 1825 to 2025, even for the 2050, the speed you can see as drastically increasing if we are shifting towards the photonics. Okay, if in contrast to the CMOS electronics. Okay, because when you are using CMOS electronics, so there is a mass of electrons and losses are more. Okay, speed is less. But if you are using all optical communication using photons with the massless particles, so you can see speed is drastically increasing. Okay, even with the plasmonics. So we can say that in the upcoming years, okay, so nanoscale structures, that this plasmonic technology is very helpful. Even if the move towards the micrometer scale structures. Okay, one micro means some photonics ring resonators or some designs are there. Okay, but still both are very helpful for the upcoming years. Okay, so only we can say delay will be less. You will have better operating speed. Okay, so same reason I have told. So limited speed. So and also diffraction. This also I have discussed in the first slide. So this basics we have studied. So because now in the next 1 hour I will focus on surface plasmon sensor. So let shift towards the first discussion on that one. Okay, so let focus on the this nanophotonic sensor. Okay, so here if you talk about this sensing, basically here the nanophotonic sensor usually work at using the refractive index phenomena. Okay, so there is a change in the refractive index. Okay, so in a air medium, and when you shift towards the sensor toward the sensing medium, so for that we are using some different, we can say, structures, simple waveguides like dielectric. Okay, as I told, or sometime metal dielectric. But there is one more advanced waveguide, so that are reported in we can say previous 3-5 years. That is the hybrid plasmonic waveguide. So what we are doing some type of hybridization in the plasmonic waveguide. Okay, so the whenever there is a plasmonic, so word is there, so it means there is a metal part and dielectric part. Okay, so some type of hybridization of the mode we have to do. For that we have to use the semiconductor. Okay, so for this, you can see the figure A. Okay, so you can see we are using metal, that is silver. Okay, and there is a dielectric SiO2. Okay, and for the doing the hybridization, so we have to use some semiconductor, as I told, like silicon. Okay, gray color part is there. Okay, and so what is the role of doing hybridization? So what once the hybridization is done, so through simulation and as well as experiment, so they have observed that you will get some better confinement, a longer propagation length, and CMOS compatibility. Okay, so so this type of waveguides also help in designing some CMOS device like modulators. Okay, so they have very good integration with the lasers, and some nanophotonic all optical chip can be designed. Okay, so I will discuss its basics, and then we will use that waveguide for the design of the nanophotonic sensors. Okay, so in this 1 hour, we will now focus on this sensing part. Okay, and as I told, so this waveguide have applications in nanophotonic device biosensing and optical interconnects, and also this type of waveguide, because of the presence of metal dielectric, we can say region, it support TM wave. Fundamental TM mode can be polarization is supported by this nanostructure. And if you see the figure B, so it is the electric field plot. Okay, so using mode, we can say RF module in a console with rough specification of, like, suppose a slot height of 50 nanometer, silicon height of 60 nanometer, and width of 20 nanometer, and it is covered with air. So you will observe that the mode propagation or confinement in the slot. Okay, so because maximum sensors are work on some slot waveguide. Okay, so this is the one example of slot waveguide as well, where you have dielectric slot, and so we can say it is a hybrid. We can say hybridization of the mode. Okay, so you will have propagation. We can say. it is a mixing of dielectric mode plus plasmonic mode in such type of waveguides. Okay, so therefore application I already told, some devices, some refractive index based sensor, some solar cell, and plasmonic antenna. So in this talk, we will focus on basically the optical sensor application. Okay, as I told, because of their advantage of confinement, better confinement, low loss at high frequency, so this hybrid plasmonic slot waveguide based sensors are favored, okay, over the simple metal insulator metal waveguide, because of more metals, the such waveguides have more loss. Okay, and even we can use it in contrast to the fiber optic sensors due to the diffraction limit problem. Okay, so next advantage is that it is CMOS compatible, compact in size, possess higher sensitivity, more field confinement in the low index region, that is the slot region, and it will also support high Q factor. So quality factor of such type of sensor is far better than the we can say simple MIM waveguide sensors. Okay, so now let's see its operating principle. So as I told, for any biochemical sensing, so we have to estimate the change in the refractive index, okay, with respect to the change in the operating wavelength. So this estimations we have to do, and we can analyze the sensing behavior. Okay, and next question is there any way of improving the sensitivity? So you can see that in a waveguide. Okay, so we can do doping, or we can add some nanoparticles, okay, in the waveguide structures, and we can enhance its operation, especially in the sensor and the solar cell. Solar cell efficiency can also be improved by using some nanoparticle or some 2D material layers as well. Okay, so like 2D materials, graphene, okay, is there some black phosphorus, all such materials can be deposited in such hybrid structures. Okay, and we can improve its efficiency. So now, in next part of discussion, I will show you few sensors, okay, nanophotonic sensors that have been reported, and how to analyze a sensor, and what are the important parameter, and what are the tools that are available, or that my scholars have used to analyze such sensors. Okay, so let first focus on this hybrid plasmonic waveguide based platform for the refractive index and temperature sensing. Okay, so for this sensors, okay, the first task is to find some resonating, we can say, structure. Okay, sometimes scholars are using ring resonators. Okay, sometimes the scholars are using grating. So means first task is to study the we can find the novel design for the resonance, and then once the resonance is there, so you know any resonating structure will give you some dip, or we can say resonance frequency, and we have to then monitor that resonance peaks, dips, okay, carefully in the presence of air and the presence of, we can say, sensing media, and then we can easily get the shift. So in this work also, we have used the resonating structure, so that is basically a V shape design, and we have used the hybrid structure. Okay, so you can see we have done the hybridization using now instead of silver, we have used gold, and then slot is there, and then we have done the doping of silicon dioxide slot, okay, with the TiO2 layer, so to enhance the, we can say, mode confinement, and then it is covered with the silicon. Red color is a silicon, and from the top you can see we can put it some sensing, we can say analyte can be aqueous type of, basically here we have sensed the benzene, so some aqueous analyte can be we can say fall on this area silicons. Okay, because later on it will go towards the porous silicon dioxide layer, and then it can affect the modes. Okay, so for this V shape hybrid plasmonic waveguide, okay, so some values, like you can say height of silicon standard we have used 220 nanometer. Okay, and slot height of slot is nearly 30, because 5 plus 25, 30 nanometer, and this can vary from 20 to 50 nanometer slot. Okay, and then we have metal. So metal height is approximately we can say 50 nanometer, and after this we have putting these values, we have used COMSOL multiphysics software, and using RF module we have done the mode analysis, right? So you can see we have excited because if you see from the front side input port, it is a rectangular waveguide, so it will support TM mode. Okay, so TM11 mode is excited and for various length. Okay, because these lengths are equal, you can say capital L is the length of the V shape arm. Okay, so for both 1000 and then we have increased to till 1400 nanometer. So what we have observed that the modes will decay out. Okay, the so because of the we can say more metal loss, you can say the strength of the field is reducing. Okay, and also there is if you take the line cut. Okay, so near the output port, so we will get the field profile. So it is a 1D profile. So we have taken the line cut across the output, and you can see the maximum mode because the modes are in the slot. It will in the slot region. So same. Using two type of simulation, that is finite element method and both FTTD. So finite element method we have used COMSOL and FTTD we have used numerical. So we have confirmed the mode confinement is in the slot region. Okay, so and then in the high index, that is the silicon, it is decay out. Okay, so all such theoretical confirmation we have verified using two type of study, FEM and FDTD. So it is supported very nicely. So next few parameters we have calculated, that is the behavior of N effective, okay, with the, respect to the width of the waveguide. So W is the width of the silicon region as well. So you can see for different slot height. So we have varied from 10 nanometer to 30 nanometer. Okay. So you can observe that once the slot height is increasing, so your N effective is reducing. Okay, so also next is the we have calculated the propagation length. Okay, so for different angles, arm angles, for because arm angle you can see theta angle is there, so it can vary from 60 to 90. Okay, so again what we have observed that the if you using 90-degree, so you will have better propagation length. Okay, so next is the effective mode area. So we have calculated the normalized effective mode area, and with respect to the we can say width of the waveguide for different angles. So here because width we have kept to 240. Okay, so maximum or 240 to 50 nanometer. So for 60-degree we have observed the better results. Okay, and you can see the maximum mode area of nearly 0.03. Okay, is achieved if you are using 240 nanometer width. Okay, so all such calculations we can do using software. Next important parameter is the loss calculation, because from this loss peak only, shift in the loss peak, we can analyze the sensor. So in this paper, we have given the relation loss. Okay, so that is basically a alpha, and it is expressed in dB per centimeter. Okay, so if you see that for different metals like silver and gold, we have used, and the loss peaks near to 1.5 micrometer wavelength we have calculated, and the more loss you can see like is for silver is there, but no doubt we have to use silver in contrast to gold is there. We have to use gold because there is no rust okay in the design, so it is our design will be robust if we use the gold. No doubt it is costly, but for design perspective we have to use the gold. Okay, so once you know this loss peak, okay, so we can calculate such loss peaks at different we can say refractive index. Okay, so of the sensing media, as I told, we can sense the benzene, okay, and other also materials, and you can observe that the loss peak is shifting, okay, towards the higher wavelength side. Okay, so this help us in calculating the shift in the peaks. Okay, and also there is a shift in the refractive index. Okay, so delta n you can see. So from this, that is shift in the wavelength divided by shift in the refractive index will give you the sensitivity. So this is the first sensor, that is the refractive index sensor. Okay, because in this paper we have discussed also about the uh, temperature sensor. So that is I will also discuss so one by one. Okay, So before that, you can see we have done the doping in the structure. So uh, doping in the structure. So let's see what is the effect of doping on the resonance wavelength. So first I have taken simple dielectric slot, SiO2 slot of 20 nanometer and then increased to 30 nanometer. Okay. And if you see that the 20 nanometer, for both slot heights, okay, so there is a shift, uniform shift in the wavelength, okay, with respect to the analyte, okay. So and if you observe once we have doping, okay, the doping layer you can use, we have used in this paper 5 nanometer and then increased to 10 nanometer, okay. And then again the same we can say resonance wavelength shift is observed with respect to the analyte. And here with doping, what you can observe, the contrast in the sensor is very better, okay, because here you will get the better contrast ratio, and we can say resolution of the sensor is very far better without we can say in contrast to the undoped sensors, okay. So next, if you can see, we have also used some polymer fitting parameters, okay. So you can see we have tried to fit our we have seen the resonance wavelength, okay, so with some theoretical model, and it show very we can say matched results. So then so we can it verified the model very efficiently. So again, in the next case, we have follow the same steps, okay, but we have varied the temperature. So we have used the heat module in the console, and we have increased the temperature from 20 degrees Celsius to the 45 degrees Celsius. You can see, and there is a again shift in the peak, okay, loss peaks. You can see from 45 degree, that is the yellow color line, to the red color line, okay. The shift is there, and we can once you vary the temperature, again there is okay, so that we have calculated through the console, that is mode analysis, and then we have put in the sensitivity formula, and then we have calculated the sensitivity. Okay, so in this way you can see the hybridization hybrid waveguides, okay, so can be used for the refractive index sensors, okay. So and also it is such waveguides, okay, because of the presence of semiconductor, doping is easy and we can improve the efficiency. Okay, so we have done some calculations, as I told, sensitivity. Okay, so both refractive index for benzene and for the temperature sensitivity. You can see that if you we have obtained maximum sensitivity of 1000, okay, 22.75 nanometer per RIU. Okay, so this is the unit of sensitivity. And for this sensor, that is with doping, you can see also the temperature sensitivity is enhanced. So from 1.98, we have achieved 2.95. So doping help us to report this, we can say, hybrid waveguide type of structure sensors. Okay. So with other, we have compared other reported sensor also. So you can see that previously it is 0.36. So there is a drastic improvement with the hybridization of the waveguide. So moreover, if you compare the refractive index, so previously it was only 612.43 in some papers and also in 77.95. So we can say hybridization and doping can be enhanced. Okay. So but we have to use some advanced fabrication steps. Okay. So this is again a challenging task. So now let discuss one more sensor. So that is basically a based upon aperture, because I have discussed in the talk uh, that there is a sub wavelength aperture and there is a some we can say extraordinary transmission through the aperture. So using such we can say an uh, for aperture based design, we have also reported uh, in IEEE Sensor Journal in 2019. So first let's focus on the design, and again and then we will see its application for the methanol sensing. So you can see this structure. So it is basically a planar structure, and as I told, for the hybrid waveguide, you need semiconductor, okay, then dielectric and metal. So this we can say design satisfies this condition. So you can see we have substrate, okay, then silicon is there, and then slot SiO2, and then metal layer. Okay, so where the hybrid modes can propagate. And again, if you see on the top, so for the methanol, we are using porous silicon. Okay, so we are uh, uh, because you need some porous material to get the interaction of the analyte. Okay, and for so that the modes can interact with the hybrid modes. Okay, so again, for this we have to deposit SiO2 and then the porous silicon. So now let's see aperture. So in the middle of the waveguide, so their aperture is there. Okay, so gray color cylindrical region, and here P1 is the input port. You can see this slot 1, and slot 2 P2 is the output port, and P3 is one more port is there where output is there, and P4. So if you see this 4-port device, okay, so it is nothing but a coupler. Okay, so input is given, then through aperture it will go through the coupling port P3, and P2 is the through port, and P4 is the isolation port. Okay, so we have used basically a coupler for designing this sensor, and there is a because of coupler design we can sense two analyte at the same time. Okay, P2 P3 will be the sensing region, so we can say sensing port. And also to improve the efficiency, so we have used the gold nano rings. Okay, so this gold nano rings we have put in the slot, so there will be some LSPR phenomena, and you will through LSPR phenomena there is the improvement in the, we can say, modes, and you will get the better intensity of the light across the coupling port. Okay, so also study we have reported in this paper. So one by one that we will analyze, and how we will do sensing we will discuss in this slide. Okay, so you can see now, first we will start with the simulation setup, because there are a few modules that are available in console for the sensor design. So for this hybrid plasmonic sensor, so we have used semiconductor optoelectronic module, because there is a semiconductor. So for putting some property of we can say indirect bandgap material, so we have to use the semiconductor optoelectronic module. Okay, so now I will tell how to put the property for metals. Okay, for metals you can use Drude model, and for silicon also. Okay, for bulk silicon, but there is a porous material like porous silicon, and for porous silicon, when analyte will interact with the porous material, so its ineffective will change. So we have to use some mathematical model. So like some Lorentz model, okay, is there a very so that we can use for the design of this structure. Okay, so for this Lorentz model, so we have used this equation. So you can see this equation will relating the ineffective with the porosity, because it is a porous material, with the uh, cladding of the we can say cladding layer, as well as the dispersed media, that is the methanol. All such things we have to put, and we can plot the plot of ineffective versus porosity. Okay, because your sensor may be 5% porous, okay, or 10% porous. So accordingly we can vary the range from 1 to like 100. Okay, so all such variations, and get the ineffective plot using MATLAB. So in this paper we have reported, and we have taken for different porosity. Okay, for different porosity we have solved and analyzed the sensor. So next, once this is done, next we have to go towards the simulation study. So that is the field profile calculation. Okay, so for this we have calculated the E field for without any gold ring, we can say, okay, across the we can say slot region, and with gold rings. So what you can observe with nano rings, due to LSPR phenomena, the strength of the field is increasing. Okay, so because once we propose this sensor, so we are struggling with the strength. You can see the strength of the field is very less. Okay, and due to the more metal loss. Okay, so to overcome this, we have put this gold nano rings, and the strength is increased. So because it is a third port, so we have to see the S31 parameter. So if you can see this S versus lambda plot, okay, so this is a scattering parameter S in dB, and with respect to the wavelength. Okay, so two different cases are there. Okay, so whenever there is a no ring and when there is a ring, so you can see that the value, that is S31, that is the coupling port, and even the S21, that is the red color line. Okay, so it is drastically improving. Okay, from we can say it is minus 12 okay, and it is improved to, you can say, -5. So through this LSPR phenomena, through this gold nano rings, first we have improved the efficiency, then we have used it for a sensor, okay, because you can see there is an improvement of 7.68 dB, okay, in the coupling power. So so once it is done, so we have done sensing. So we have varied the porosity of silicon region from 20 to 45%. Okay. So and we have then extracted their field plots. Basically, we have taken the cut across the coupling region only, and you can see there is a fields strength in the slot of this coupled port is more. Okay, with as compared to the silicon region. Okay, and once for also what thing we can observe that once you are increasing porosity, so your modes will decay out, moving from red color to green color, that is 20% to 45%. Strength of the field will also reduce, okay, because of it will decay out if you are using the bigger pores. Okay, so next is the analysis of sensor. Okay, so methanol sensing we have done with different porosity. You can see first one is the case for 20%. Okay, so we have again calculate the coupled power. So S31 versus lambda. Okay, so that we have uh, considered and in percentage. So uh, so from 0 to 100%, we have put the scale. So I'm showing here till 40%. So you can see that the in the presence of air, one peak is there, and for methanol, the peak is reducing and shifted. Okay. So through this shift delta lambda and also delta n, we can see because in air and methanol difference. Okay. So and then take the ratio, we can get the sensitivity. So it is nearly 77.95 nanometer per RIU. And if you see the figure of merit, one more parameter is there. That is the ratio of sensitivity versus the full width half maximum. So for this case, it is 17.51. And also next, similarly, we can do other case like 25%, 45%. Okay. And we can get the values for the these two parameter. And but the maximum value we are getting with lower porosity, because at higher porosity your modes will decay out, it will become more lossy. Okay, and it is also tough to confine the modes with more porous structure. Okay, so next I want to discuss one biosensor. So it is basically a DNA hybridization that is reported in one journal. And as I told, so this same hybrid structure we can use for biosensing design. So means in the first I have shown you temperature, and then methanol, that is some volatile alcohols, and now this is the third application, that is the biosensing. And here some challenges are there, so therefore I have pick up this sensor as well in this today's talk. Okay, so one by one we will study, and we will see what are the few challenges, and what once you overcome, and then we will can realize such type of nanoscale sensor that will have a better we can say application in the biosensing side. Okay, so again if you see the design, so it is basically a single resonating biosensor, and it is again a hybrid plasmonic slot waveguide. Okay, so you can see in this design also they are using hybrid modes. Okay, for single and dual resonating refractive index based sensor. Okay, and basically DNA hybridization, there are two type of we can say strands are there, SS and DS. Okay, and so this both strands have different refractive index. Okay, so in this paper all such one table is given where material permittivity and refractive index are reported. Okay, so next same question is how to get the sensitivity. So same we can say operating principle, that is we have to calculate shift in the wavelength and change in the refractive index. Okay, and once it is known, we can get calculate the device sensitivity. So same equation is valid here, but how to start, so let one by one we will see. And what is the importance of now software tools, okay, in this biosensor as well we will discuss. Okay, so first point is the calculation of n effective. Okay, so if you see this diagram, that is a single resonating biosensor. Here again they are using SiO2 as substrate. Okay, and next they are covering it with gold layer, okay, and they are making these two arms, okay, so that they can hold the sample. So blue color is a sample, and here they are putting water, okay, and then there is a we can say silicon. So after that you have to make some two pillar like of structures, okay. So graphene no, sorry, so this is silicon that is covered with the linker layers. So this dark color gray line is a linker layer, so that will link the DNA, we can say molecules from the H2O to the your silicon waveguide. Okay. So for this, you can see once it is uh, uh, the linking start take place. So red color is nothing but your DNA. So that will start with the help of linker. It will covering the silicon waveguide. Okay. So this is the basic structure. And again, if you talk about thickness of metal, so it may vary from 50 nanometer, okay, to the 100 nanometer, okay. So such basic, we can say, dimensions we can use for this structure. And again, it is a different, as I told, the DNA is there, then linker layer is there in silicon. So first task is to calculate the N effective value, and using the we can say RF module of console, we can get the N effective value. Okay, so in the presence of ssDNA and dsDNA, okay, so black and this red color line, and also we have to take the difference, okay, delta n. So same we can calculate delta n effective, okay, for this case for different slot width, okay. So this we can, because we have to we are using again slot waveguide, so for different slot widths we can get this value. And we can put in a simulator. For example, slot width is 100 nanometer. Okay, so it can, we can see, so we can use at 1.5. Okay, so here 1.515. Okay, so all such things we can take it and put in a simulator across the we can say material properties. So next, let's see what is the single resonance cavity structure and dual cavity, and then I will show you the mode profile. Okay, so you can see they are using the slot waveguide here, and they are making this resonating structure. Okay, here you can see this is a single resonating structure. Okay, so here if you observe, okay, what thing is that there is the input port, okay, output port, and next is the uh, dual cavity. So for getting dual cavity, so you will get some dual slots here also, and this structure will resonate at particular frequency. And how to get, we have to simulate this structure over a band of wavelengths like 1550 nanometer to 1500 to 1600 nanometer we can simulate. So I can show one by one there field profiles, first for simple design in presence of air, and then in the presence of ss DNA and ds DNA, and then we can see the sensing performance. Okay, again, first let focus on single resonance cavity structure. Okay, so as I told, they are using here single uh, uh, slot region here for this single cavity region. Okay, and once you simulate, so these are the top view A and B. Okay, so if you see this electric field profile for biosensor, okay, so as I told, we have to use wide band. Okay, so 1500 to 1600, or even if the dip is there, so we can start from 1350 to 1650. Okay, so very clearly one resonating peak will come, and once you put a different N effective value for ssDNA and dsDNA, so we will get the two response, that is black and red color line. Okay, so also clearly you can see there is a shift in the both DNA. So such shift we can calculate, okay, because it is dependent upon refractive index. Okay, so that we can say the ratio of shift in the wavelength by refractive index will give you the sensitivity. Okay, so if you see the mode profile, so they have reported in two different peaks. Okay, so one is the maximum transmission where there is no resonance, that is 1360 nanometer. Okay, so approximately this point. Okay, and in the second B, so you can see it is resonating because of single slot, it is a single resonance structure. Okay, so you're not getting any output. Okay, so at nearly 1535.7 nanometer here. Okay, so resonance is there. So it confirm, we can say, both frequency response and mode analysis. And Once it is done, we can calculate various parameter like figure of merit, okay, Q factors for this design. And so next is the dual resonance cavity. So you can see that if you are using two slots in the resonant cavity area, so it become dual resonance cavity. Okay. So here first you can see there is no resonance. Okay. So your input is going to output. Okay. So next that is if you taking the uh, we can say electric field response at 1558.6 nanometer, so means resonance peak. Okay, so it will resonate, so you can get due to dual resonance structure, you can say dual resonance take place here in this region. Okay, and you will get no output. So again it is in accordance with the frequency response behavior. Okay, and again for both DNA there is a shift. Okay, so means it is supporting the we can say sensing behavior at in this window. Okay, in between 1400 to 1600 nanometer. And now let's see their performance, which is better. Okay, so single slot or dual slot cavity is better. Okay, so let's see one by one. So as per their numeric values for the sensitivity. So if you see the sensitivity value, so for single, we can say resonance cavity. So it is 90.4 nanometer per RIU, whereas for dual cavities, okay, so it is at 1370 nanometer per RIU. Now the reason is that if you are using more cavity, so there will be some heat loss. Okay, so always there is some uh, heating will be there if you are moving toward dual or triple or okay quadruple resonance cavities. So therefore, due to heating, the performance will be reduced drastically. So what after this challenge, so what they have reported in this paper that try to used lower resonance cavity in the nanophotonic structure. Okay, so that the heating region can be as minimum as possible. Okay, so all such we can say challenges are there for the biosensor also. So now I will discuss the last structure. So that is reported by my MTech student recently. And here we have done the ethanol sensing. Okay, so this is the work that is reported in IEEE Sensor Journal. And here we have used again the hybrid structure, okay, but the CMOS compatible design. So that is the novelty for this nanostructure. So one by one we will see. So first I will show you the design and then we will discuss with the starting point. Okay, so now for CMOS compatible, we need some CMOS compatible materials. Okay, so you can see here we are using copper. Okay, so that is CMOS compatible. And so moreover substrate is there, then we have to deposit the copper. Okay, and again now instead of using porous silicon on the top, so we have used porous silicon deposition over the copper and then cover it with the dielectric. So we have modified the design and then cover it with the copper. Okay, and then we have made some sensing region and put some analytes. The harmful volatile alcohols like ethanol is exposed through this sensing region. And so if you want to see the top view, if you take cut across x dash there, so you will get this copper region and the slot, and then porous silicon slot and copper. So this type of waveguide you will get for the this hybrid plasmonic structure. Okay, now with this porous structure, this ethanol vapor can easily condensed. Okay, and it can go towards the dielectric modes and it can affect the we can say the dominant modes, and we can see what is the shift in the we can say the in the transmission. So for this, let see how this operates. Okay, like what are the few important technical terms regarding to this sensor. Okay, so for this, as I told, we have to calculate the N effective. Okay, for this design again due to the multi-layer structure, and your N effective will affect the propagation constant beta. Okay, of the traveling waves. Okay, so here K naught is basically a mode vector in a vacuum. So you can see this N effective, how it controlling the propagation constant, and it will uh, result in the shift in the transmission, right? So same thing we have put in a flow chart. You can see that there is a change in the effective mode index, then there is a change in the propagation constant, and then there is a change in the light wave characteristics. So means due to this only there is a shift in the wavelength. You can see from blue to the red, there is a shift will be there when it interact with the ethanol vapors. Okay, so such we can say uh, uh, this type of, we can say, nanostructures we have reported, where we have also calculate some redshift, okay, using the console software. And you can see that the surface plasmon resonance frequency, uh, same standard relation we have used. Okay, so it is omega p divided by square root of 1 plus epsilon d, where d is the dielectric permittivity, right? So next, if you see, so same uh, like parameters we have calculated. So one additional parameter of Q factor we have reported in this paper. So sensitivity, same relation, that is change in wavelength, change in refractive index, and then figure of merit is the ratio of sensitivity of full width half maximum. And here additional parameter Q factor we have report. So it is relating the resonance wavelength divided by the full width high maximum, full width half maximum. Okay, so that we have used and calculated for our design. Okay, so this is the structures that we have simulated. So now I will show you the results. So these are the rough dimensions and the materials that we have put in the simulator. Okay, so you can see width is we have fixed to 300 nanometer. Okay, and then rest are the other parameters for the copper sensing aperture. Okay, all such we have reported in the research paper. And also you can see the electric permittivity at 1550 nanometer. Okay, so metal have negative. Okay, so minus 113.02 for copper, and for silicon it is 11.7, and silicon dioxide 4.2, and cladding air 1. Okay, so that we have put in a simulator. So we have started with dispersion relation. So where we have seen what are the dominant modes and we can say radiated mode in our structure. So this is the corresponding, we can say, dispersion plot. Okay, so instead of omega k, we have now converted to beta frequency. So for different waveguide widths. Okay, and here you can see from this frequency we can easily get the cutoffs. So for 300 also nanometer, it follow the cutoff condition. So for because our is 193 point, I think 1 terahertz. So clearly it shows some dominant modes. So through dispersion relation, we have validated the dominant modes. Okay, and then we have used again the Lorentz model because it is a porous material. So and because it is in the we can say core of the waveguide, so we have put additional parameter, that is the volume fraction. Okay, so it is because within the waveguide, so this parameter is we have put in this for this structure. And then using again MATLAB. Okay, so we have simulated it. Now the how the refractive index of ethanol is varying with wavelength. So for this we have to use the Selmer's equation. So these equations we have used for ethanol. Okay, so various constant B, C, D, E we have put uh, in the this equation, and then with the help of MATLAB, so we have got these graphs for different porosity. Okay, so you can see now the refractive index of porous silicon is varying with the uh, porous silicon porosity from 0 to 100. Okay, and similarly, what is the equivalent refractive index with respect to the volume fraction V? Okay, so blue color line is the same variation for different porosity. So for these values, we have put in a simulator console. Okay, so and we have done we can say RF simulations, electromagnetic, using electromagnetic theory. Okay, so you can see for different porosity from 10, 15, 20, 25, right? For both air and ethanol. So there is a shift in the peak, redshift will be there, okay, for different porosity. And we have again calculated the parameter sensitivity, figure of merit, and Q factor, okay, for different porosity like 10 to 25. And here you can see that maximum sensitivity of 612.4 nanometer per RI we have got, and maximum Q factor is 52.9. So there is a drastic increase. Okay, so increase in the Q factor as well for this design. Okay, so few more result I want to discuss about the field plots. So you can see there is a TM polarization. So you can see there is a dependence of aperture, okay, we can say sensing region on the design as well. So as I told, we have used 300 nanometer because if you have faded modes, means this is a radiated mode, okay, so this is not a dominant mode. So we have to use as per the cutoff dispersion relation. So for we have seen that for 300 nanometer, so we are getting cutoff. So you can see now the modes are going very nicely, okay, for this type of structures, okay. Even if you start increasing, so 400 nanometer, and for this structure also, due to this reason only, we have started from our analysis from this 300, okay, because after below this there is a decay out of the modes, then 300 to 400, and same we have confirmed through the field plots. This is surface plot of electric field in the volt per meter, okay. So that is matching our result with the simulation. And also we have seen their strength. So we have taken the vertical, we can say horizontal cut, horizontal cut across the center. And then this is the same behavior of field, electric field volt per meter versus the axis, okay. And maximum strength is with the 400 nanometer. Okay, so that we have reported. And next is the dependence of slot height. Okay, so also we have started with the 10 nanometer, and then we have observed that from 20 nanometer. Okay, so it is supporting the modes across the complete structure. Okay, so below that it is not guiding very nicely. And next is we have also reported to 30 nanometer. So where you can see the modes are going across the porous region as well. So therefore, we have can say that from 20 nanometer to 30 or maximum to 50 nanometer, we can use the slot height. Okay. So similarly, we have also validated through line cut also. So we have taken the horizontal cut and calculate the strength. So maximum we can see that 20 nearly 28 volt per meter. Okay. So we are getting with blue color, that is the 20 nanometer, okay, slot. So also study we can do using finite element method based console simulator. Okay, so last discussion is about fabrication. So how such sensors can be fabricated. So you can see we have to start with the substrate, then copper deposition, because as I told, it is CMOS compatible if you are using copper instead of gold. Okay, so next is again we have to deposit silicon, and then we have to, this is the important step, that is electrochemical etching. So this through this only we can decide the porosity. So once you do electrochemical etching, so we are doing the converting silicon to porous silicon. Okay, and then we have to use the hard mask. Okay, and then we can etch out the remaining we can say region. And after that, doing the etching, you will get the porous silicon in the rectangular waveguide form. Okay, and next is deposition of SiO2. Okay, so you can deposit SiO2 over the porous silicon and then cover with the copper. And again, we have to create some sensing region. So again, we have to use the hard mask, and the we have to use the etching process to etch out the desired metal layer, so that we can get the exposure of this sensing region to the ethanol vapors. Okay, so for simple silicon deposition, we can use the standard method like plasma enhanced CVD. Okay, such standard methods we can use for the design of this CMOS compatible ethanol sensors. Okay, so this is the experimental setup that we can use. We can use some tunable laser source, and that can excite this sensor. And then we can use some inlet outlet for the we can say movement of the ethanol vapors or volatile organic chemicals. Okay, so next we have to use EDFA because the modes will fade out, and then we can use some we can say coherent detector or integration can be done. That is basically a frequency domain integration can be done. Okay, so now this is the we can say performance of the sensor. So with 10% porosity, sensitivity of 400.43 nanometer per RIU can be achieved, whereas Q factor of 46.8 and cutoff frequency is 132 terahertz. Okay, so this cutoffs can be we can say calculated using the dispersion relation. Okay, so now let summarize with the advantage of this nanophotonic sensor. Okay, so we have observed that in contrast to fiber optic biosensors, or we can say this nanophotonic sensor provide various advantage because of CMOS compatibility and on-chip laser, we can say label-free sensing. So the sensor that I showed, that is the DNA hybridization, is basically a on-chip label-free sensing. Okay, so next advantage is high sensitivity, a low limit of detection, low crosstalk, strong detection, multiplexing capability. Means we can also do multiple sensing at the same time. Okay, then high stability and immune to electromagnetic interference, and also small size and low cost. So these are the few advantages. Okay, and now let's see what are the challenges in this design of the nanophotonic sensor. So because of small structures, so they have limited sensitivity. So nano fabrication is very difficult, and also losses in this resonance based sensors are very we can say tough to handle, because here energy is transferred into heat if you're using the cavities. Okay, so next is also sometimes instrument for this nanophotonic effects are much bigger and costlier. So also sometimes disturbance in the surrounding also can also affect the performance of this sensor. And more last point is stability. So stability basically, if you talk method, also affect the excitation of surface plasma polytron. So we have to you can see we have various methods starting from prism to the grating. So based upon application, or we can use some stable design like gratings. Okay, so these are the few reference that I have used for this talk. Okay, and thank you. So in 15 minutes now, if you have any questions, you can ask.
I think very elaborate. You have given the talk very elaborate. So question might not be there. So only one question I want to know, sir.
Yes, madam.
Can you hear me, sir? Yeah. So MIM, when you are telling metal, insulator, metal, or DMD, dielectric, metal, dielectric. So in case of SPR, MIM or DMD, which one is better for higher sensitivity?
No, it again will depend upon the interaction with the analyte. Okay, so if you are using dielectric on the top, okay, so in that case, analytes can be easily interact, because dielectrics are porous in nature. It can go, and but if you need more confinement, okay, so then MIM is better. Means it depend upon the application. For device, MIM is better, but for sensor, dielectric, metal dielectric is better.
So in your lab, whether fabrication is possible for DMD or MIM?
Yes, ma'am, I mean the starting phase, like if you have planar structure, like I have shown you, like metal dielectric metals, it's possible, and characterization can also be done in CRF. There is central search facility. Planar structures, simple planar structure, madam.
So you can like suppose our scholar want to go there and they want to do the fabrication. It is possible. Basic DMD or basic MIM.
Madam, you can first share the structure. I told you, no, structure. If you can see, I can tell you whether it is possible, because if some planar design is there, then it can possible, madam. Grating based, it is tough.
Just one layer by layer deposition.
That is possible, madam. You can, but NOC is required, madam. NOC you can share from your HOD.
That can be taken. That can.
Yes, madam. Yes, madam.
Okay. Thank you so much.
Okay,
Thank
madam.
you for such an
Thanks.
elaborate.
Okay, thanks. Okay, thanks for inviting us. Take care.
Jara sir.
Yeah.
Jara,
Thank you, sir. Thank you very much for providing a deep
you
set of nanophotonic sensors.
Yes. Kindly all of you mute.
இல்ல நான் போட்டோ வச்சிருந்தேன் கையில ஓகே
Hello.
சொல்லிட்டா கலர் பிரிண்ட் எடுக்கலாம்னு போய் எடுத்து சொன்னாங்க
Okay, Jairaj sir, you
அந்த
wind up.
காலேஜ் கடைசியில பெங்களூர் ஒரு காலேஜ் அது
Okay, I'm ending the meeting.
Jairaj sir, next time if you will find if anybody's speaker is on, kindly remove them from the meeting. Okay? It's disturbing because
That is all.
people are not understanding. So better if they are not interested, you remove from this meeting.
எக்ஸாம் எழுதிருக்கேன் அதுக்கு அப்புறமா தான் போச்சு
Sure, sure.
எல்லாம் அங்கதான் எழுதணும்
Understand, Jairaj sir?
என்
Yeah,
டீட்டெயில்
ma'am.
இல்ல அப்படின்னு
So you have identified now, na? Next time you just
Yeah,
don't allow them.
yes.
Okay, Jairaj sir,
So
continue.
shall we end, ma'am?
Yeah.